Hello again. In our previous lesson, we graphed sine and cosine, okay? And we found out that cosine theta, sine theta are essentially x and y, okay? We also found out that these graphs are wave type graphs. Now we're going to graph other trigonometric functions, especially tangent, secant, cosecant, and cotangent. So first of all, we need to begin with the quick rules. Tan x has a period pi and the vertical asymptotes where the cosine of x equals 0. And we say that because tan theta is equal to sine theta divided by cosine theta. So the way to think about it is we have y over x. So where cosine x equals 0, we get what is called a vertical asymptote, which in other words, we get a dotted line, okay? Meaning that it approaches there, but it never touches, okay? Secant x is equal to 1 over cosine x. Notice secant x is the reciprocal of cosine, so the reciprocal of it would give you 1 over cosine x. And cosecant x is equal to 1 over sine x, and the reciprocal of sine x would give you this. So it's essentially cosecant being the reciprocal, giving you the reciprocal of 1 over sine x, okay? Then cotangent x is cosine x over sine x, or in other words, way to think about it is cotangent theta go to cosine theta over sine theta, which is the same as saying x over y. And then where sine x is equal to 0, right here, if sine x is equal to 0, then you also get a vertical asymptote, okay? You get a vertical asymptote if sine x is equal to 0. So asymptotes and periods are the main graphing feature, right? And so typically we are going from pi, or excuse me, typically you go from 0 to 2 pi, okay? That's typically how the parent behaves in when you're graphing the parent functions of a trigonometric function, okay? All right, so let's head on down to example number 1. So it says graph y equals tan x on negative pi over 2 and pi over 2. State the period, the vertical asymptote, and 3 key points. Okay, so tan x has a pi, or excuse me, has period pi, which is what we said earlier up here. Tan x has a period of pi. So when we're thinking about this, the first thing we want to do is divide by cosine. Okay, so tan x, we have the function y tan x. So that's essentially saying tan x is equal to sine over cosine. Okay. So the tangent is undefined when the cosine is equal to 0 on the interval from negative pi over 2 to pi over 2. So the cosine equals 0 at the endpoints. Okay. So the vertical asymptotes would be these two guys, right? So x equals negative pi over 2 and x equals pi over 2. These would be the vertical asymptotes. Okay. The tangent function has a period of pi. So the period, remember, is basically where it crosses the x-axis or at the peak, the max, the min, things like that. Okay, so we have a period of pi. Now we need to identify 3 key points. Okay. So in order to identify three key points at x equals 0, tan of 0 is going to give me 0. So that point would be located at 0, 0. So I'm just going to sketch this graph here for a moment. Okay. So we already established, first of all, that we do have vertical asymptotes. The vertical asymptote would be negative pi over 2. So that means that would be negative pi over 2 here. And then that would be pi over 2 there. Okay. So those are our vertical asymptotes. And then we already established that if x is 0, if we substitute 0 into tan, we would get 0, 0. Okay. At x equals pi over 4, what would tan be? The tan of pi over 4 would be equal to 1. Okay. So the tan at pi over 4, remember this is a half, so a fourth of the way would be here. So this would be pi over 4. And then the output would be 1. So that would be here. Okay. And then if we do at x equals negative, let's go a fourth of the way over there. At x equals negative pi over 4 as well. So tan at negative pi over 4 would be negative 1. Okay. Then from there, that point would be located at we got negative to be negative pi over 4, a fourth of the way there. And then the output would be negative 1. So that would be put that here. Okay. So the way this would look, remember this vertical asymptote tells me the behavior of the graph. So I'm going to say the way this graph would look, I don't want to mess up this sketch. Let's see. So I'm going to cross the origin here. I don't want to mess this up because I only, so I want to get close to, so like that. Make okay. So it simply kind of like, you can see it kind of turns. This is essentially what the parent graph for y equals tan looks like on these two intervals, okay? With these 3 key points, okay? So essentially the 3 key points would be negative pi over 4, comma, negative 1, 0, 0, pi over 4, comma, 1, okay? And again, if we're interpreting the graph, it rises from left to right and then continues upward, okay? So as it approaches the vertical asymptote, x is equal to negative negative pi over 2 to the left, it approaches the vertical asymptote. It approaches the vertical asymptote for pi over 2 on the right. Okay. And remember, it approaches it, but it never touches it. Okay. And again, this is the parent function y equals tan x with a period of pi. Okay. All right, let's continue. So example number 2. Example number 2 says y is equal to 2 tan x minus pi over 4. Now notice there's a shift in this x here. Okay, so this question is going to ask us, it says state the period, shift, vertical asymptotes, and then one central point. Okay, so that's all we need for the problem. So again, the parent function is y is equal to tan x, and the parent function has a period of pi. So in this equation, the coefficient of x, as you can see, is 1. So what does that say? That says, first of all, it's inside the coefficient of x inside the tangent is 1. So the period is going to stay this. Okay. So if it was something different, then we would have to compute for the period. So again, the period problem, or the period, how do you calculate the period? You take pi and you divide it by the absolute value of b. So in this case, b is going to be equal to 1. So the period stays pi. Okay. Now identify the shift. Okay. Now we're going to identify the shift. The expression for the shift is here, x minus pi over 4. So that expression, x minus pi over 4, explains a right shift of pi over 4. That's simple. Okay. So we're going over a fourth of the way to pi. That's essentially how you interpret that. The central point for the parent of a tangent is where it crosses 0, as we looked at the last problem. So that's 0, 0. After shifting to the right, pi, a fourth of pi is going to be the central point. It's going to be the new central point, okay? So the central point with that shift is now going to be, so remember it's 0, 0. So now the new central point, after it takes on that shift, is going to be pi over 4, comma, 0. And then this coefficient here tells us what happens with the graph. This graph is going to have a vertical stretch. So the graph is steeper, okay? Or I can say more slender. It's less wide, right? But the central point is going to remain the same, okay? So we have a vertical stretch by a factor of 2. Now, we need to find the vertical asymptotes. So the parent tangent graph has vertical asymptotes, as we looked at previously, vertical asymptotes of x equals negative pi over 2 and x equals pi over 2. Those are the vertical asymptotes of the parent function. Now, notice we have a shift here. So we're shifting from the vertical asymptotes that we originally have in the parent function. So again, this is the parent. So if we're shifting over, right, then the new location, the new parent location would end up here, right? So with this new parent location, we can simply calculate it using algebra. So that would be negative pi over 2 plus pi over 4. Finding common denominators, that would give us negative 2 pi plus pi over 4. I consolidated the numerators. That's going to give me negative pi over 4. So that's 1. And then the next part would be pi over 2 plus pi over 4. And keep in mind, I'm just adding the shift to the previous vertical asymptote. Finding common denominators, it's going to give me 2 pi over 4 plus pi. And I'm going to consolidate them, which is going to give me 3 pi over 4. So the new vertical asymptotes are x equals negative pi over 4 and x equals 3 pi over 4. So the final answer is we have a period of pi, right? Because it did not change. Because that b, right? Remember, a, the trigonometric function, parentheses, b of x, well, b would be 1, right? So that's why we got the parent of pi, because in order to find the parent, that's pi divided by the absolute value of b, with b being 1. We simplify this, the period would just be pi, okay? So we have a period of pi, and then we have a shift right here of pi over 4. Then we have the new asymptotes of negative pi over 4, x, and then, or x equals negative pi over 4, and then x equals 3 pi over 4. Right? We also found that the new central point move after the shift to pi over 4, comma 0. All right? Try the pause and try problem at the bottom. Okay, so the equation is y equals tan parentheses 2x. Find the period in two consecutive vertical asymptotes around x equals 0. Okay, so we have y equals tan 2x. Now here, b is equal to 2. So the period is pi over the absolute value of b, which is pi over the absolute value of 2, pi over 2. Okay, so we have the period, and just keep in mind the the, the way this looks, and we've been working on these, would be, let's just say in this case it's y a and parentheses. Okay, so that's how we know that b is 2 in this case. Okay, just recall that from the previous lectures. So we got the period, and we can, let's see, now we need to move on to the vertical asymptotes, because we had to find the period and then two consecutive vertical asymptotes around x equals 0. All right, so tangent is undefined when its when its inputs are equal to one another. Okay, so tangent undefined when inputs equal. Okay, so what does that look like? So we'll start with pi over 2 plus k pi. Now, the input here is 2x, as you can see. So remember, that would be what's happening with the x, right? So essentially, that is 2x equals pi over 2 plus k pi. To find the asymptote closest to the right of 0, we need to use k is equal to 0, all right? So we're going to use, I'm going to say, okay, we need to use k is equal to 0 over here, right? So if k is equal to 0, what does that look like? That looks like 2x equals pi over 2. Then we can multiply both sides by 1/2 to get rid of this 2 over here. That leaves us with x equals pi over 4. So to find the asymptote closest to the left of 0, we need to use k is equal to -1. Okay. Now, that would be 2x equals pi over 2 minus pi. From there, we can compute this by giving common denominators. 2x, that would be pi over 2 minus 2 pi over 2, which simplifies to negative pi over 2, 2x. Again, multiplying by 1/2, x is equal to negative pi over 4. So two consecutive vertical asymptotes around x equals 0 would be x is equal to pi over 4 and x is equal to negative pi over 4, where the period is pi over 2. Okay, let's continue. Example number 3. Use y equals cosine x to sketch y equals secant x on interval 0 to pi. State where secant x is undefined. Okay, so here we're using cosine x. What we need to do is we need to understand that secant x is equal to 1 over cosine x. Okay, so secant would be undefined when this is equal to 0, when the denominator is equal to 0. So on the interval 0 to pi, cosine equals 0 at x is equal to pi over 2, and at x is equal to pi over 2. Okay. Now, secant x is undefined at x is equal to pi over 2 and x is equal to 3 pi over 2. Those values become the vertical asymptotes. Okay, these are the vertical asymptotes as well. Okay, where you would have to sketch the dotted line, see what that would look like. Okay, now we use important cosine values. Okay, you remember from our previous lecture, the cosine values are very common, and cosine, for example, cosine at 0 is equal to 1. So the reciprocal would be 1 over 1, which is equal to 1. Okay, so cosine at 0 is equal to 1, which means secant at 0 would be 1 over 1, right? because that would be, so it's 1 over cosine x, or cosine 0. Cosine of 0 is 1. So this would be what it would look like there. Matter of fact, 1. We have our first point essentially, right? That first point would be 0, 1. Then we have cosine pi, which is negative 1. So the secant of pi, or the secant of pi, would be the reciprocal of that. So that would be 1 over negative 1 is negative 1. Right? And then let's do another one. Let's cosine of 2 pi, because that's where it would be 1 there. So secant of 2 pi would be 1 over 1, which is 1. So again, this point, write the point down for this point, was pi 1. This point would be pi. So the secant graph has branches that sit above y is equal to 1 and below y is equal to negative 1. So in other words, if I were to sketch this graph, okay, if I were to sketch this graph like this, recall the cosine x, right? The cosine x would be a graph that looks like this, where the first period would be here, right? Because 0, 1, so it would be here, then it would come 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 here. Okay, so essentially it would look like this. Okay, that's how cosine x looks. So when you think of this graph and the reciprocal of it, it would actually, first of all, the vertical asymptotes would be pi over 2. So pi over 2 would be located here, right? So pi over 2 would be located here. So then what would happen is you would have essentially a vertical asymptote there. So the reciprocal of this graph would look like this. Okay. And likewise, when you get here, it would look something similar. Just because this one right here would be, so this would be pi over 2, pi over 2, then this would be pi, then this would be 3 pi. So that 3 pi over 2 is why the vertical. So these two vertical asymptotes, this would be 3 pi over 2, and then this would be pi over 2, right? So those vertical asymptotes that we computed here, just to show you what they look like. And so that's why, again, the reciprocal, you wouldn't touch those vertical asymptotes, but this is showing you why those vertical asymptotes would exist here once we sketch it. And then, of course, this would go to pi, 2 pi. And so if we wanted to graph this, we could obviously continue to graph it using these points here, 0, 1, and 2 pi over 1 and pi over pi of negative 1. Okay, that's why we ended up getting right here. So this would be pi of negative 1, right? So it's showing you that this period would end up being here, and then 2 pi of 1 would end up right here. Okay, 2 pi of 1 pi, put it right here, which is why this would end up like this, right? If we were to sketch it, it would look like that right there. Okay, and again, that's the reciprocal of cosine x, which is secant x. Okay, all right, let's continue. There's more that can be said there, obviously. Okay, so example number 4. Explain how the zeros of sine relate to the vertical asymptotes of y equals cosecant x. Give the asymptotes. Okay, here in example 4, first of all, you need to understand that the cosecant is the secant of sine, is the reciprocal of sine. So cosecant of x is 1 over sine x, right? So 1 over sine x, and that means that sine is the denominator. Sine x is the denominator. So whenever sine equals 0, cosecant would be undefined, right? So it would have a vertical asymptote. So again, whenever sine equals 0, cosecant is undefined. So sine x equals 0 up here. Then what happens is you have okay is undefined. Now we're looking at this from the interval that we looked at earlier, 0 to 2 pi, because again, this is a parent function. Now, on that, sine equals 0 at 0 at x equals 0. Then again, at x equals pi. And then again at x equals 2 pi. Okay. So I do have a reference here I can show you really fast. So again, sine looks like this, right? So where sine is 0, we have 0, 0. At 0, it's 0, 0. At pi, it's going to be 0. And then at 2 pi, it's also going to be 0. Okay, so that's sine theta, or sine is a function of x, right? Now, in terms of the reciprocal, these become the vertical asymptotes for y is equal to for the for y is equal to cosecant of x. Okay, so again, x equals 0, x equals pi, x equals 2 pi. So the zeros for sine become the vertical asymptotes for cosecant. Okay, so this happens because cosecant is 1 divided by sine, right? So when this is 0, that makes this undefined, and that essentially is how we know what the vertical asymptotes is. So if sine is 0, then cosecant would require division by 0, which is essentially undefined. Okay, let's look at a common mistake. A student draws y equals secant x as a wave crossing the x-axis. Explain why secant x never equals 0. So a student, okay, so first of all, this is incorrect because secant is not a sine wave. Okay, remember, sine and cosine are sine waves, right? Um, Secant is the reciprocal of cosine. Okay, familiarize yourself with the reciprocals as well. So we have essentially this is secant x equaling 1 over cosine of x. Okay. Secant x equals 1 over the cosine of x. For a fraction to equal 0, the numerator must be 0, but the the numerator must be 0, but the numerator of secant, you can see, is always 1. So if we said 1 over cosecant of x is equal to 0, right? So the numerator is 1, not 0. So secant x can never be equal to 0. It never crosses the x-axis. So, I mean, also, in addition to that, secant is undefined when the cosine equals 0. And what that does is that creates a vertical asymptote. So secant x never equals 0. The range of this particular problem would be y is less than or equal to -1, or we could say y greater than or equal to +1. Okay, so secant should be drawn with separated branches, not as a smooth wave crossing, right? The final review, I know this was a lot, but you need to understand, you need to remember this, that tan theta is equal to sine theta over cosine theta, or y over x. Tan x has a period of pi, very important. Tan x also has vertical asymptotes when the cosine is equal to 0. Same thing for cotangent. When sine is equal to 0, then there's a vertical asymptote. Familiarize yourself with these reciprocal functions, right? You don't get they don't get very intense in precalculus, but they can, depending upon the type of problems that you see, type of problems that you'll be given. But they'll get more rigorous as you get into Calc 1. All right. That completes video 13, part 1, graphing other trigonometric functions. Thank you, and hope to see you in the next one.